Now let's look at integrals involving powers of the tangent and the secant. Now I'm only going to do tangent and secant. Please note that cotangent and cosecant follow the exact same pattern. The only difference is that their derivatives would be negative. Before I talk about this, I want you to recall that the derivative of the tangent is equal to the secant squared, and that the derivative of the secant is equal to the secant times the tangent. And all of these should be times a u prime, so let me just add that in. Number 10, the indefinite integral of tangent cubed x secant squared x. Secant squared x, well, isn't secant squared just the derivative of the tangent? Yes, so if you have a secant squared, then you're a power of the tangent. You are, again, a power of the tangent. Why? Because if you let u equal the tangent of x, its derivative would be secant squared of x dx. Since the derivative is secant squared of x dx, and that's exactly what you have, then this just becomes u cubed du, which you can integrate. That's just u to the fourth over 4 plus c, getting out of u's and back into x's, tangent to the fourth of x over 4 plus c. For number 11, secant to the fourth tangent of x dx. Notice I have tangent here, and it's raised to the first power, and I have secant, and it's raised to a power that is more than 1. So I can rewrite this secant as the secant cubed of x times the secant of x, because secant cubed times secant is secant to the fourth, and then times the tangent of x dx. Why is that helpful? Because if you think about it, this guy right here, secant of x tangent of x, is the derivative of the secant. So that makes you a power of the secant. You would let u equal the secant of x, and then the derivative would be secant of x tangent of x dx, and that would give you u cubed du, which you know integrates as u to the fourth over 4 plus c, getting out of u's and back into x's, secant to the fourth x over 4 plus c. For tangents, we're trying to find a secant squared so we can become a power of the tangent. And for secants, we're trying to find a secant tangent so that we can become a power of the secant. Now, here are some general guidelines for powers of the tangent and the secant. And the reason that they're general guidelines is that sometimes none of this is going to work and you're just going to have to do something completely different. And we're going to look at that in examples 14 and 15. Here are our general guidelines. If you have secant, and secant is an even positive power, you save a secant squared, and then you change everything else into tangent using the Pythagorean identity. Remember that Pythagorean identity is secant squared theta is equal to tangent squared theta plus 1. If you have tangent and it's an odd positive power, you want to save a secant tangent for your du, and then change the remaining tangent terms into secants using a Pythagorean identity. And remember that Pythagorean identity is that tangent squared theta is equal to secant squared theta minus 1. If all you have is tangent all by itself raised to a positive even power, you got to convert to secant and then save a secant squared to become a power of the tangent. And lastly, if all you have is secant raised to an odd power, you have to use integration by parts, just like we did in example 10 from section 8.2. Now these are guidelines, and the reason that they're guidelines is it's possible to have a problem where secant has an even positive power and tangent is odd and positive, so you get to choose which one you want to do, Or, like I said, what we're going to see in 14 and 15, none of this is going to work, and we're going to have to think outside the box a little to find our indefinite integral. Let's look at the first two using these guidelines. If I look at number 11, I have secant to the fourth x tangent squared x. Well, this first thing says if secant is an even positive power, well, secant is an even positive power. What it wants me to do is save a secant squared. So I would write secant squared x tangent squared x times secant squared x dx, because secant to the fourth is just secant squared times secant squared. Then I have to change the remaining secant terms into tangent using the Pythagorean identity. So instead of writing secant squared x, I have to write tangent squared x plus 1. And then I still write tangent squared x and secant squared x dx. Once I've done that, then I let u equal the tangent of x, because if u is equal to the tangent of x, the derivative du would equal secant squared x dx, which is perfect because that's what I have. And then I come over here and I rewrite this as something in u's, and we're looking at the indefinite integral of u squared plus 1 times u squared du. First distribute your u squared, then integrate. So we're looking at the indefinite integral of u raised to the fourth plus u squared du. Integrating, we get u to the fifth over 5 plus u cubed over 3 plus c. Finally, getting out of u's and going back into x's, we end up with tangent to the fifth of x over 5 plus tangent cubed of x over 3 plus c. What about number 12? Number 12 is tangent cubed of x, secant of x dx. Well, the first thing said if secant is raised to an even positive power, I don't have that. The second one, if tangent is an odd positive power, well, tangent is odd and positive in this case. Since tangent is odd and positive, I have to save a secant tangent. So I rewrite tangent cubed as tangent squared x, and then secant of x, tangent of x dx, because I know that tangent squared times tangent is my tangent cubed. Now that I've saved that secant of x, tangent of x, I have to change the remaining tangent terms into secants using the Pythagorean identity. So I know that tangent squared x is really secant squared x minus 1, so I can rewrite this as secant squared x minus 1. And this is still times the secant of x, tangent of x dx. Now we let u equal the secant of x. If u is equal to the secant of x, then the derivative du would equal secant of x, tangent of x dx. Then we know that this then becomes u squared minus 1 du. And this is something we can integrate. Integrating, we get u cubed over 3 minus u plus c. Getting out of u's and going back into x's, we end up with secant cubed x over 3 minus secant of x plus c. What about number 13? Number 13 is tangent cubed of pi x secant to the sixth of pi x dx. Well, this actually meets both number 1 here and number 2. Secant is even and positive, and tangent is odd and positive. So this has tangent is odd and positive, and secant is even and positive. So we can do it either the way we did for number 1 or the way we did for number 2. And it doesn't really matter which way, we will get 2 different answers, but they're equivalent if we would just do some work with Pythagorean identities. What I typically tell students is I look to see which exponent is smaller, and then I use the one with the smaller exponent. Since 3 is smaller than 6, I'm going to treat this as what I do when tangent is odd and positive. When tangent is odd and positive, remember you save a secant tangent, so I rewrite this guy as tangent squared of pi x, secant to the 6th of pi x, tangent of pi x dx. But I need not secant to the 6th times tangent, I need secant tangent. So I keep going here. This is really tangent squared of pi x, secant to the 5th of pi x, and then secant of pi x, tangent of pi x dx. Now I have that secant tangent that I needed. Then I have to change the rest of the tangents into secants. So we rewrite tangent squared of pi x as secant squared of pi x minus 1. Still times secant to the 5th of pi x, secant of pi x, tangent of pi x dx. Now what we need to do is make the substitution. If u is equal to the secant of pi x, the derivative would be pi times the secant of pi x, tangent of pi x dx. Well, I don't have pi times that, so I divide by pi, and 1 over pi du would equal the secant of pi x, tangent of pi x dx. Moving over to the right-hand side, this here then becomes the indefinite integral of u squared minus 1, and then u to the 5th, and then 1 over pi du. Now I need to distribute u to the 5th, and then I can integrate. Distributing u to the 5th, I end up with u raised to the 7th minus u to the 5th du. Integrating, we get 1 over pi times u to the 8th over 8 minus u to the 6th over 6, and then plus c. Distributing the 1 over pi and getting out of u's and back into x's, we end up with secant to the 8th of pi x over 8 pi minus secant to the 6th of pi x over 6 pi plus c. Now, if we would have saved a secant squared, if we would have done it the other way around, if we would have ended up with this being tangent cubed of pi x, and then we would have had secant to the 4th of pi x, secant squared of pi x dx. And then we would have changed this guy here into tangents. And I'll do that just really quickly. That would have been a tangent squared pi x plus 1 quantity squared. And we would have done the sub here for tangent. This answer actually is tangent to the 8th of pi x over 8 pi plus tangent to the 6th of pi x over 3 pi plus tangent to the 4th of pi x over 4 pi plus c. So this answer and this answer are equivalent. Using Pythagorean identities, we could get them to look exactly the same. Both answers would be correct on an exam or in the homework.